Forensic engineering is a specialized discipline that investigates failure, accident, and incident involving technical or engineering aspect. Its main objective is to provide fair and reliable judgment regarding the root cause of this incident and ensure public safety. Forensic engineers conduct inspection and examination of structure, material, product, or system to identify the relevant element and the root cause of failure. They combine their understanding of engineering theory, material science, physics, and other related disciplines in a multidisciplinary approach. To piece together what happened and identify the source of failure, forensic engineers gather information from document evidence, interview witnesses, and utilize various testing and analysis techniques. They work across different engineering subdisciplines such as structural, civil, mechanical, electrical, and material engineering. Overall, forensic engineering is essential for protecting public safety. It helps identify faults, improve the design and construction process, and ensure proper maintenance of engineering systems and parts. By understanding the root cause of accident and failure, forensic engineers assist in preventing similar accidents from occurring again. Forensic engineers combine engineering theories, method, and analysis to investigate failure and accident, provide fair judgment, and improve public safety in various industries.
Syarikat Bina Masjid Enterprise has been given the responsibility of constructing complex Sekuan Dewan Badminton by University Teknologi Marah UiTM. The estimated cost of the project is approximately around 1,713,245.22 ringgit. The project is being privately funded and the university is not contributing any fund towards its completion. The work begin on 1st January 2018 and it was completed. The purpose of conducting this case study is to examine and investigate the structure flaw present in the building. For the purpose of this case study, the rebound hammer method has been selected as the means to investigate and comprehend the factor contributing to the failure of the complex Sukan. Cracking. At time to construct the building, concretized hammer are commonly referred to by various names including rebound hammer, Swiss hammer, and Schmidt hammer. Flexible instruments are utilized for the assessment of the state of hardened concrete. Concretized instruments have a wide range of applications beyond their common use in estimating the in-place compressive strength of concrete. The assessment of concrete structure or pavement extends beyond its strength, encompassing various other factors. The portability and user-friendly nature of hammer, coupled with their extensive historic usage, have contributing to a comprehensive understanding of their performance and outcome. Rainfall, temperature, and earthquake are some of the major natural sources of structure failure. Wind speed, and etc. These natural variables may come into play gradually or unexpectedly, and/or structure may be built to accommodate this factor. An earthquake is caused by a sudden release of energy in the earth crust, which causes seismic wave. Earthquake cause shaking and, in some cases, displacement of the ground of the earth's surface. If seismic protection are not followed during design and construction, there are a few reasons why the precast concrete at the site crack. Poor maintenance is the first factor. It is necessary to perform regular maintenance on a structure following a specific duration after its initial construction has been completed. Certain structures may require an early assessment of their deterioration issue, where others can exhibit long-term durability based on the quality of their design and construction. In addition, the regular application of external paint of the building serves as a means of safeguarding the structure from potential damage caused by moisture and various chemical agents. The application of waterproofing and protective coating on reinforcement steel or concrete serves as a second protective measure. The effectiveness of this measure is contingent upon the quality of the concrete. Next, poor construction phase. There are a wide range of construction techniques that causes of concrete to crack. Inadequate construction methods are typically brought on by ignorance, carelessness, avarice, or irresponsibility. Primary reasons for inadequate construction methods are: first, choosing a wrong material; second, selection of inexpensive, low-quality material; third, inadequate and incorrect mixing of mortar, concrete, and other mixed components; fourth, control issue at many stages of the manufacturing of concrete, including batching, mixing, transportation, putting finishes, and curing. Fifth, overload brought about by construction are typically more severe than those brought by service. Sixth, large void, honeycomb, and crack brought on by poor quality control and supervision ultimately accelerate to deterioration of concrete. Seventh, improper build joint between successfully pour of concrete between a concrete structure and masonry.
My name is Syahma Mati Muhammad Fauzi, and I'm going to continue with Chapter 3, which is Systematic Investigative Program. So, what is Systematic Investigative Program? A systematic investigation is an activity that involves a prospective plan that entails a thorough or careful examination on and has or involves a prospectively identified approach to studying a particular subject, responding to a particular question, testing a particular hypothesis, or developing theory based on a system, method, or plan. Professional study, interview or survey study, group comparison study, test development, interventional research, and the analysis of identifiable data or biospecimen are example of systematic investigation. Field tests on a concrete slab are carried out to determine the strength of the concrete in the case study. It gives some idea about the strength of concrete based on rebound hammer and touch. I'm going to continue with the procedure of investigating. The first step is a preliminary meeting to define the goals. This stage is to verify the equipment checklist in line with the activities to be performed. Here is where the rebound hammer was chosen. Next, secure the scene, mark the specific location, and define the procedure for the device chosen. Now, after the investigation has been issued, collect the data based on the investigation. After that, pack the equipment properly and send it to the laboratory. Continue the process by preparing a report and with the recommendation and action that need to be taken. After all, close the project. Now, I'm going to continue with the procedure of conducting tests on a concrete slab using rebound hammer in the case study. Step 1 is to choose a location for the investigation, and complex sukan was chosen. After that, we will continue with choosing a specific location and marking point for 9 reading at 3 different places. Figure 3.2 shows the process of marking the point using a pen and ruler. Next, put gentle pressure on the plug to unlock it from the lock position and help it expand to the test ready position. By keeping the instrument perpendicular to the test surface, press the plunger against the concrete surface. If the hammer doesn't blow, gradually increase the pressure. Record the data that is being collected. Repeat the procedure for another 2 points. Finally, we continue with the result of our investigation. There are 3 points of location that are marked, namely point A, point B, and point C. As you can see in this slide, there are 9 readings for each point, and the data that is being collected is namely rebound hammer, rebound value, and compressive strength. As far as I can conclude based on the data collection, the average rebound value is between 20 to 40, which the quality of concrete considered a fair and good layer. While average compressive strength can be seen in this slide, point A is 8.22 Newton per meter square, point B is 15.89 Newton per square meter, and point C is 24.78 Newton per square meter. The inclination angle chosen is 90 degrees because the sample of the experiment is a slab. That's all from me, and thank you.
Assalamualaikum and hi, my name is Wan Muhammad Arif Safwan bin Wan Aziz. I will present the finding in our case study. The sport complex of UiTM Sri Iskandar Architectural Design findings emphasize the value of adhering to established guidelines and design codes. So the first point on design aspect is insufficient reinforcement. Insufficient rebars may make the slab prone to cracking, especially when subjected to strong loads or temperature changes. Next is inadequate joint placement. The slab may break in unexpected places if joints are not placed correctly or if their spacing is too broad. Besides that, insufficient subgrade preparation. The slab may move differently and break if the subgrade is not correctly prepared or compacted, causing this uneven settlement. Other than that is inadequate load distribution. This might happen if heavy machinery or point loads are not adequately taken into consideration in the design. So then, lack of control joints. The slab may randomly break in unfavorable places if control joints are not sufficiently present or if their spacing is excessively broad. For construction aspect, the study additionally explore how a sport complex is built, concentrating on the procedures, techniques, and issues to think about when doing it physically. Construction aspect must follow conformity to the standard of work practice and specification. The first point on the construction aspect is improper concrete mix design. Shrinkage and cracking or less resilience to environmental pressures might result from a poorly formulated mix. Next is insufficient curing. A weak slab prone to cracking can be produced by insufficient or incorrect curing practice, such as inadequate moisture retention or early removal of foam or curing materials. Besides that, improper compaction. Concrete not properly compacted during placing may develop voids, honeycomb, poor consolidation. Other than that, is overloading during construction. During construction, high loads on the slab, such as the storage of bulky construction supplies or heavy machinery, can lead to overstressing and cracking. Then poor formwork and support. The formwork might bend under the weight of the concrete if it is not sufficiently supported or braced, leading to an uneven or weak slab that is more likely to break. In addition to design and construction, the study also examined a sport complex environmental aspect. The first point on the environmental aspect is temperature changes. The slab expands when the temperature increases and compresses as the temperature falls. Next, moisture variations. The amount of soil beneath the slab might alter depending on the moisture content. When the earth is moist, it enlarges and contrasts as it dries out. Besides that, chemical exposure. Over time, concrete can degrade as a result of exposure to certain chemicals, such as de-icing salts, oil, or acidic substances. These substances may penetrate the slab surface, weakening and increasing the likelihood of cracking. Other than that is poor drainage. The slab may settle unevenly and break as a result of the increased moisture content weakening the subgrade or promoting erosion. Then, vegetation growth. As neighboring trees or plants swell, their roots may put on a strain on the slab. If the roots pierce the concrete, this pressure may cause the slab to move or break.
For the root cause and complex ukai, two major factors has been selected. Rainfall and soil movement are two natural factors has been the greatest impact on the causal structure fracture. El Nino has been assumed to be the cause of the extreme weather that occur in Malaysia right now. Then, failure of structure can be also attributed to the two factors: inadequate maintenance and improper material selection. Low quality material and specification are also causes for the material selection. At the specification, the non-standard are
In a case study of complex sukan in UiTM Sri Iskandar, forensic engineering was used to investigate a structural flaw. The study revealed design aspect and construction-related factors that contribute to floor slab crack. It emphasized the importance of adhering to guidelines, codes, and regulations to ensure structural integrity. In conclusion, forensic engineering provides valuable insight into failure and accident. By applying engineering principles, conducting thorough investigation, and collaborating with experts, forensic engineers contribute to public safety and prevent future incidents. The case study highlights the significance of design and construction consideration in engineering projects. Crack failure in structural components pose serious concern for reliability and safety. To address this issue and reduce risk, several recommendations can be implemented. Firstly, conducting comprehensive inspection and assessment of susceptible components is essential. This includes examining material, manufacturing process, and operating conditions to identify factors contributing to crack. Performing a detailed root cause analysis helps identify underlying factors responsible for crack failure. This involves examining material properties, design flaw, manufacturing defect, and operational stress to implement corrective action. Material selection should prioritize enhanced fracture resistance, including non-destructive testing to help identify potential defects or inconsistencies. Advanced engineering principles, stress analysis, help to identify high stress area. Advanced manufacturing techniques such as precision finishing and controlled heat treatment enhance structural integrity. Applying stress mitigation techniques like surface treatment and stress relieving process reduce crack initiation. Stress redistribution throughout design and modification disperse load concentration. Regular inspection, including visual inspection and structural analysis, help detect crack at early stage. A comprehensive maintenance plan with repair or replacement strategies ensure long-term system integrity. Preventive measures and technological remediation procedures are crucial in mitigating the risk associated with crack failure. By following this recommendation, organizations can reduce the occurrence of crack failure, enhance product reliability, and prioritize user safety.